Greetings and salutations, dear viewers. Get ready for some fantastic content. Hello, dear viewers. Get ready to expand your horizons as we delve into notation for differentiation. In differential calculus, there is no single uniform notation for differentiation. Instead, various notations for the derivative of a function or variable have been proposed by various mathematicians. The usefulness of each notation varies with the context, and it is sometimes advantageous to use more than one notation in a given context. The most common notations for differentiation and its opposite operation, the antidifferentiation or indefinite integration, are listed below. Now, let's redirect our focus towards Leibniz's notation and discover its significance in our narrative. The original notation employed by Gottfried Leibniz is used throughout mathematics. It is particularly common when the equation phax is regarded as a functional relationship between dependent and independent variables, and Leibniz's notation makes this relationship explicit by writing the derivative as advantageous. Furthermore, the derivative of at is therefore written advantageous or advantageous or advantageous. Higher derivatives are written as advantageous, and this is a suggestive notational device that comes from formal manipulations of symbols, as in advantageous. The value of the derivative of at a point may be expressed in two ways using Leibniz's notation. Advantageous or advantageous. Leibniz's notation allows one to specify the variable for differentiation in the denominator. This is especially helpful when considering partial derivatives. It also makes the chain rule easy to remember and recognize. Advantageous. Leibniz's notation for differentiation does not require assigning a meaning to symbols such as or known as differentials on their own, and some authors do not attempt to assign these symbols meaning. Leibniz treated these symbols as infinitesimals. Later authors have assigned them other meanings, such as infinitesimals in non-standard analysis, or exterior derivatives. Commonly, is left undefined or equated with x, while is assigned a meaning in terms of via the equation advantageous, which may also be written, e.g., differentiation. See below. Such equations give rise to the terminology found in some texts wherein the derivative is referred to as the differential coefficient, i.e., the coefficient of. Some authors and journals set the differential symbol in Roman type instead of italic. The SOIC 80,000 Scientific Style Guide recommends this style. Get ready to immerse yourself in the world of Leibniz's notation for antidifferentiation as we examine its impact and relevance. Leibniz introduced the integral symbol in Analyso's Tetragonistique pars secunda and Methodi tangentium inversa exemplar, both from 1675. It is now the standard symbol for integration. Begin aline. Int x int cirx fax c0 y c0 int x int fax c1 I int x int left int x right int x times x fax int fax x c2 underbrace int dots int n I underbrace x dots n int underbrace times dots times x in fax int sax cn. Endoline. In this section, we'll be deep diving into Lagrange notation, unraveling its complexities and uncovering valuable insights. X. One of the most common modern notations for differentiation is named after Joseph Louis Lagrange, even though it was actually invented by Euler and just popularized by the former. In Lagrange notation, a prime mark denotes a derivative. If f is a function, then its derivative evaluated at x is written. Fax. It first appeared in print in 1749. Higher derivatives are indicated using additional prime marks, as in fax for the second derivative and fax for the third derivative. The use of repeated prime marks eventually becomes unwieldy. Some authors continue by employing Roman numerals, usually in lowercase, as in 5x, 5ox, 5x, to denote fourth, fifth, sixth, and higher order derivatives. Other authors use Arabic numerals in parentheses, as in fax. This notation also makes it possible to describe the nth derivative, where n is a variable. This is written. Phonics. Unique characters related to Lagrange notation include: when there are two independent variables for a function fax, y, the following convention may be followed. Beginnerline. F prime frat partial x f x f prime frat partial y f y prime frat partial x f x f prime frat partial y partial x f x e f prime frat partial y f I. Enderline. As we move forward, let's uncover the untold stories and fascinating intricacies of Lagrange notation for antidifferentiation. Padding left Emacs substyler padding left Emacs. When taking the antiderivative, Lagrange followed Leibniz's notation. Faxa faxx widex. However, because integration is the inverse operation of differentiation, Lagrange notation for higher order derivatives extends to integrals as well. Repeated integrals of f may be written as fx for the first integral. This is easily confused with the inverse function fx. Fx for the second integral, fx for the third integral, and fnix for the nth integral. As we enter this new chapter, let's navigate the complexities of denotation and unravel its multifaceted nature. This notation is sometimes called, although it was introduced by Louis Franois Antoine Arbogast, and it seems that Leonhard Euler did not use it. This notation uses a differential operator denoted as d operator or Newton-Leibniz operator. When applied to a function, it is defined by ertx faxitx. Higher derivatives are notated as powers of d, where the superscripts denote iterated composition of d, as in d for the second derivative, d for the third derivative, and d for the nth derivative. Denotation leaves implicit the variable with respect to which differentiation is being done. However, this variable can also be made explicit by putting its name as a subscript. If f is a function of a variable x, this is done by writing dx for the first derivative, dx for the second derivative, dx for the third derivative, and dxn for the nth derivative. When f is a function of several variables, it is common to use a stylized cursive lowercase d rather than as above. The subscripts denote the derivatives that are being taken. For example, the second partial derivatives of a function are a beginnerline partial x f frat partial x x e f frat partial I partial x f frat partial x partial y partial I e f frat partial I enderline c. Denotation is useful in the study of differential equations and in differential algebra. Moving ahead, let's uncover the hidden gems within denotation for antiderivatives and discover their significance. Denotation can be used for antiderivatives in the same way that Lagrange notation is as follows: dfax for a first antiderivative, dfax for a second antiderivative, and dnfax for an nth antiderivative. Let's now enter the realm of Newton's notation and discover the fascinating stories it has to tell. Isaac Newton's notation for differentiation, also called the dot notation, fusions, or sometimes, crudely, the Flisbeck notation for differentiation, places a dot over the dependent variable. That is, if y is a function of t, then the derivative of y with respect to t is y. Higher derivatives are represented using multiple dots, as in Newton extended this idea quite for Newton's notation reproduced from s to fifth derivatives, Quadratura Curvarum Newton, 1704, page 7 in original MS. First to seventh, nth and nth derivatives, Method of Fusions Newton, 1736, 313, 318 and page 265 p. 163 in original MS. First to fifth derivatives, A Treatise of Fusions Maturin, 1742, page 613. First to fourth and nth derivatives, Articles Differential and Fusion, Dictionary of Pure and Mixed Mathematics, Peter Barlow, 1814, first to fourth, 10th and nth derivatives, articles 622, 580 and 579 in the History of Mathematical Notations, Figari, 1929, first to sixth and nth derivatives, the Mathematical Papers of Isaac Newton, Vol. 7, 1691-1695, D.T. Whiteside, 1976, and 17, first to third and nth derivatives, A History of Analysis, Hans Niels Jank, 2000. 84-85. The dot for nth derivative may be omitted. Chauversitany. Beginnerline dati equifractite fract right fracturbigal dati bigra fracturbigal terbigra equal d y equal yt oversit I adotati equifractite equal d y equal yt oversiterdity I oversit I editati equifractite equal d y equal firm ed equal it oversiterdity editoversit I dotati editotati equifractite equal d y equal firm vert equal it oversiterdity I over oversitire equifractite equal d y equal firm vit equal it oversiterdity adot oversitire equifractite equal d y equal firm viet equal it oversiterdity editidity equifractite equal d y equal firm xert equal it oversiterdity equifractinitatin equal dten y equal finert equal iron tenderline. Unique characters related to Newton's notation include replaced by combining diaresis plus combining dot above replaced by combining diaresis twice. Newton's notation is generally used when the independent variable denotes time. If location is a function of t, then y denotes velocity and y denotes acceleration. This notation is popular in physics and mathematical physics. It also appears in areas of mathematics connected with physics, such as differential equations. When taking the derivative of a dependent variable y equal fax, an alternative notation exists. A fractitidix ditidix a equifractit fractxit a fractfractit fractxit a fractix a fractxer bigel faxer bigger equal dy equal fx equal y. Newton developed the following partial differential operators using side dots on a curved x. Definitions given by Whiteside are below. Beginnerline. A mathcox fixie, dot mathcox frac partial x x. A mathcox dot I frac partial y f y. Becoen a mathcox text or a dot left dot mathcox side frac partial x f x. A mathcox a text or a left mathcox guitarite dot I frac partial I f I. The dot mathcox dot frac partial x partial y c f x c. Enderline. In the next portion, we'll be immersing ourselves in the realm of Newton's notation for integration and examining its broader implications. Newton developed many different notations for integration in his Quadratura Curvarum 1704 and later works. He wrote a small vertical bar or prime above the dependent variable, a prefixing rectangle, or the enclosure of the term in a rectangle to denote the fluent or time integral absment. Beginnerline. Y box doti equivalent doti dinfert dt dt wift c0 yt c0 oversita prime box y equivalent y dinf dt wift c1. Enderline. To denote multiple integrals, Newton used two small vertical bars or primes, or a combination of previous symbols, to denote the second time integral absity. Chauversita prime a box oversita prime equivalent oversita prime inf equal dt y equal plus c. Higher order time integrals were as follows. Newton's notation for integration reproduced from first to third integrals. Quadratura Curvarum Newton 1704, page 7 p. in original MS. First to third integrals. Method of Fusions Newton 1736. 265 266 p 163 in original MS. Fourth integrals. The Doctrine of Fusions James Hodgson, 1736. 54 and 72 first to second integrals, articles 622 and 365 in A History of Mathematical Notations, Figari, 1929. The nth integral notation is deducted from the nth derivative. It could be used in Methodus Incrementorum Directa and in the Saarbrück-Taylor 1715. Beginnerline. Oversit the prime box oversit the prime equivalent oversit the prime int dty c3 oversit the prime box oversit the prime equivalent oversit the prime int dty c4 oversit and oversit the prime box oversit and I oversit the prime equivalent oversit and I oversit the prime int street dt and y street cn. Enderline. This mathematical notation did not become widespread because of printing difficulties and the Leibniz-Newton calculus controversy. In this section, we'll be shedding light on partial derivatives and its impact on our understanding of the subject. When more specific types of differentiation are necessary, such as in multivariate calculus or tensor analysis, other notations are common. For a function f of a single independent variable x, we can express the derivative using subscripts of the independent variable. Beginnerline. fx Enderline. This type of notation is especially useful for taking partial derivatives of a function of several variables. Partial derivatives are generally distinguished from ordinary derivatives by replacing the differential operator d with a symbol. For example, we can indicate the partial derivative of with respect to x, but not to y or z in several ways. A frac partial x equal fx partial x f. What makes this distinction important is that a non-partial derivative such as a text-style frac f may, depending on the context, be interpreted as a rate of change in f relative to x when all variables are allowed to vary simultaneously. Whereas with a partial derivative such as a text-style frac partial x, it is explicit that only one variable should vary. Other notations can be found in various subfields of mathematics, physics, and engineering. See for example the Maxwell relations of thermodynamics. The symbol left frac partial to partial the right s is the derivative of the temperature T with respect to the volume V while keeping constant the entropy subscript S, while left frac partial to partial the right P is the derivative of the temperature with respect to the volume while keeping constant the pressure P. This becomes necessary in situations where the number of variables exceeds the degrees of freedom, so that one has to choose which other variables are to be kept fixed. Higher-order partial derivatives with respect to one variable are expressed as a beginnerline a frac partial of partial x equal fx a frac partial of partial x equal fx enderline, and so on. Mixed partial derivatives can be expressed as a frac partial of partial x equal fxc. In this last case, the variables are written in inverse order between the two notations, explained as follows. A beginnerline and fxy equal fxc a frac partial I left frac partial x right a frac partial of partial I partial x enderline. So-called multi-index notation is used in situations when the above notation becomes cumbersome or insufficiently expressive. When considering functions on Rn, we define a multi-index to be an ordered list of n non-negative integers, alpha equal alpha l dot sulfur and alpha ions ergic. We then define, for a Ferrento x, the notation partial alpha f a frac partial alpha a partial x alpha a dot a frac partial alpha and partial x and alpha in f. In this way, some results such as the Leibniz rule that are tedious to write in other ways can be expressed succinctly. Some examples can be found in the article on multi-indices. Prepare yourself for an eye-opening discussion on notation in vector calculus in the upcoming portion of this video. Vector calculus concerns differentiation and integration of vector or scalar fields. Several notations specific to the case of three-dimensional Euclidean space are common. Assume that is a given Cartesian coordinate system, that it is a vector field with components a x, a y, a z, and that x, y, z is a scalar field. The differential operator introduced by William Rowan Hamilton, written and called del or nabla, is symbolically defined in the form of a vector. A nabla left frac partial x frac partial I frac partial z right, where the terminology symbolically reflects that the operator will also be treated as an ordinary vector gradient. The gradient grad of the scalar field is a vector, which is symbolically expressed by the multiplication of an scalar field. Beginnerline operatorn grad varphi lf frac partial varphi partial xer frac partial varphi partial I frac partial varphi partial zerite lf frac partial partial xer frac partial I frac partial zerite varphi another var. Finally, divergence. The divergence div of the vector field is a scalar, which is symbolically expressed by the dot product of and the vector. Beginnerline operatorn under the math for partial x over partial x partial y over partial y partial z over partial z left a frac partial x a frac partial y a frac partial z right. We got a math for now we got a math for endolineal Laplacian. The Laplacian div grad of the scalar field is a scalar, which is symbolically expressed by the scalar multiplication of and the scalar field. Beginnerline operatorn biv operatorn grad of varphi naba got naba varphi naba got naba varphi delta varphi. Endolineal rotation. The rotation curler or rotor of the vector field is a vector, which is symbolically expressed by the cross product of and the vector. Beginnerline operatorn mutual a math for left partial a z over partial a y over partial z partial a x over partial z over partial x partial a y over partial a x over partial y right left partial a z over partial a y over partial z right a math phi left partial a x over partial a z over partial x right a math left partial y over partial a x over partial y right a math begin matrix a math phi and a math kick frac partial x and ik frac partial y and ik frac partial z a x and a y and a z end of matrix number times a math for endolineal. Many symbolic operations of derivatives can be generalized in a straightforward manner by the gradient operator in Cartesian coordinates. For example, the single variable product rule has a direct analog in the multiplication of scalar fields by applying the gradient operator, as in Many other rules from single variable calculus have vector calculus analogues for the gradient, divergence, curl, and Laplacian. Further notations have been developed for more exotic types of spaces. For calculations in Minkowski space, the Zerlemmert operator, also called the Zerlemmertian wave operator or box operator, is represented as, or as when not in conflict with the symbol for the Laplacian. I appreciate your time and I'm grateful for every like, comment, and share.